Hello, everyone. Good morning, good afternoon, good evening, wherever you are. Welcome back to the second edition of Fundamentals of Solid Formulation webinar series. This is a 7-week webinar series organized by XLPI and JSTAR Research with a webinar every Wednesday starting from April 7th and ending on May 19th. We have 7 experts from the industry, starting from Henry Morrison from Gilead, who gave the first webinar on the topic of correlation of drug substance bulk properties to predict and troubleshoot the formulation of drug product. Then we had Dr. Sudhakar Garad from Novartis talking about the importance of solid formulations and bioavailability during R&D. And today we have Dr. Luca Isolino from Merck, who's going to talk about solid state modeling and its role in drug development. And then we have Dr. Daniel Joseph Price from Millipore Sigma, who's going to talk about amorphous formulations for solubility enhancement, risk, and opportunities. So these are the 4 webinars lined up for April. And then going into May, we have 3 webinars starting from Luca Russo on May 5th, going to talk about current practice and future perspective in crystallography for API solid form risk management. Then we have Dr. Alish Medek from Vertex, who's going to talk about application of solid-state NMR to differentiate and quantify different API amorphous phases in complex tablet formulation. And finally, we'll have Dr. Adam Keats from Syngenta, who's going to talk about crystallization in agrochemicals, the good, the bad, and the unusual. So, as I mentioned before, this FSF 2021 is organized by XLPI and JSTAR Research. XLPI is an algorithm-driven artificial intelligence-based pharmaceutical technology company with sites in Boston, Beijing, Shenzhen, and Shanghai. JSTAR Research is an innovative CRO based in New Jersey and is an independently managed subsidiary of Poton. Poton is a contract development and manufacturing organization based in China. These 3 organizations are strategic collaboration partners in pharmaceutical drug design and preclinical development programs. My name is Sivakumar Segran. I'm the Senior Director of Business Development at XLPI in Boston, and I'm going to be your moderator today. So before we kickstart the webinar today, I just want to give you a brief recap of what happened in the last 2 weeks. And for those who have missed the webinar, attending the live session, you can always go back to our website, xlpi.com, and if you click under the events page, you can find FSF 2021. And there, if you click on the play button next to the speaker names here, then you can watch the recordings. You just have to fill out a form, as you can see below, and put in your name, affiliation, email ID, and then it'll take you to the next page where you can just watch the recordings. And along with the recordings, we also posted a Q&A page where questions that were not answered during the live session are answered by the speaker and then posted along with the recording on our website. So pretty much everything is captured for you to watch the recordings from the comfort of your home or office. So today, we have webinar number 3, and our speaker today is Dr. Luca Isolino from Merck. And Luca is a senior scientist, and he's a computational chemist. And Luca provides expertise in solid-state modeling and is involved in a variety of drug development projects in close partnership with experimental collaborators at Merck. Today, Luca will show how solid-state modeling, including crystal structure prediction and virtual co-crystal screening methods, are employed at Merck to support drug development projects, and how its integration with experimental efforts has made it a vital component in the solid form selection process. And the title of Luca's talk is Solid State Modeling and its Role in Drug Development. So before I hand over control to a speaker, I just want to address the audience. Please use the questions tab to send in your questions today. And don't wait for the speaker to finish the presentation, because questions will be taken on a first come, first served basis, and we are likely to have 15 minutes of Q&A session. So, and please also put in the slide number to which you're referring to, then that would allow the speaker to handle the questions and also take in some additional questions depending on the time we have at the end. Okay, so without further ado, let me hand over control to our speaker, Dr. Luca Isolino from Merck.
Can you see correctly?
Yes, we do.
Okay, thanks Shiva for the introduction. And before starting, I would like to thank, of course, the organizer for inviting me to talk today, and the audience for joining in and listening to this presentation. So this presentation will be about solid state modeling and its role in drug development. Why is solid form selection important in drug development? The reason is that several properties of molecular materials are solid form dependent. The same molecule packed in different ways in the solid state can have the remarkably different properties. Here is a list of properties that can differ between different solid forms of the same molecule. And in the green boxes, I'm showing some that are of particular relevance to the pharmaceutical industry. Of course, different solid forms can have different solubility, which can lead to different bioavailability. And last week's talk by Sudhakar Garat shows the importance of bioavailability, which is extremely important, of course, for formulation. Different solid forms can have different particle morphology, different tensile strength, compactability, tabletability, which are very important for processing and manufacturing. Different dissolution rates, which is very important in determining how a drug is absorbed into the body, and different physical and chemical stabilities. And having a chemically unstable formulation can lead, for example, to toxin degradants, which is something undesirable. So selecting the right form is extremely important. Hence, solid form screening is a key component of drug development. And what solid form screening does is attempting to find and characterize all the possible solid forms of a given molecule and select for development a stable one with optimal properties. I would like to put my emphasis on stable, because if the chosen form is not stable, late form changes can be catastrophic. And I believe most of you will be familiar with the case of ritonavir as a very striking example of how problematic a late form change that is unpredicted can be. So the same active pharmaceutical ingredient molecule, or API, upon crystallization can form several neat polymorphs, so different arrangements of the molecule with itself, without any other constituent in the solid state. And each of them can have, of course, different properties. On top of that, a molecule can also crystallize with water to form hydrates, or with other solvent molecules to form solvates. And sometimes other multi-component crystals are explored to improve properties. For example, salts, where an API crystallizes with a coformers and they're both in a charged state, and a co-crystal, where both the API and the coformer are in a neutral state. I'm not going to talk today about amorphous formulations, which can be important, and Daniel Price's talk next week will talk about that, but this talk will be focused on crystalline formulations. So how can modeling help? Experimental screens aimed at finding all the solid forms of the molecules are costly, time-consuming, and most importantly, do not have a clear endpoint. There is no point in time where you can say that enough experiments have been performed to cover all possible crystallization conditions and to cover all the possible packings of a given molecule. There is no set of experiments is guaranteed to find everything. And solid state modeling can help streamline the process to get from a given candidate molecule to a viable pharmaceutical product. So the first use of solid state modeling I would like to talk about today is the use of crystal structure prediction of CSP or CSP as a tool for solid form de-risking. So what is CSP? CSP is a set of techniques that aims to find all the thermodynamically stable form of a compound starting from the chemical diagram only, from the molecular diagram only. So starting from the molecular diagram, CSP allows to get a crystal energy landscape, which is a set of predicted unique crystal structures of a given compound ranked on their thermodynamic stabilities. So each of these points in this landscape is a predicted structure. The lowest energy one is predicted to be the most stable, and the alternative ones are predicted to be metastable relatively to the global minimum in thermodynamic energy. How does CSP actually work in practice? In most cases, the thermodynamic stability is approximated by lattice energy at 0 Kelvin. Lattice energy is the energy required to separate the molecules in a crystal to an infinite distance in their lowest energy conformations. Lattice energy is dominated by weak intermolecular interaction, and so an accurate assessment requires costly electronic structural calculations. There are many successful CSP methods, and several of them calculate lattice energy via dispersion-corrected density functional theory. And the most accurate dispersion-corrected density functional theory methods have a relatively low error bar in the relative rankings of predicted forms of approximately 1 kilojoule per mole. On top of calculating lattice energy, the addition of the vibrational component to free energy at finite temperature calculated with the harmonic approximation has been shown in the literature to be able to improve the accuracy of the predicted stabilities relative to experimental data. However, we cannot get straight from a molecule to a ranking calculated with electronic structural methods. And the CSP generally requires a hierarchical process. So one starts with a molecule and then tends to perform a global search where all the possible packings of the molecules are generated, and a preliminary energy ranking is obtained, but given that the lattice energy surface is immense and that thousands of crystal structures can be generated, this preliminary lattice energy ranking is generally obtained with force fields, not with electronic structural calculation method. And this force field can either be transferable or tailor-made for a given molecule. Only then a cutoff in energy is applied, and the crystal structures that are lower than this cutoff in force field energies are taken forward, and more accurate calculation and re-ranking are performed, and in this case, electronic structural calculation methods are employed, calculating the wave function for the crystal structure. Even with this hierarchical process, CSP can be extremely expensive, and for a pharmaceutical molecule, it can easily take hundreds of thousands of CPU hours, which is a very high burden, and for this reason, CSP needs to be used when it's needed and very deliberately. How can CSP help drug development? CSP can help right-size experimental screening efforts, guaranteeing that the number of experiments that are performed is not too small, but also not too large for a given aim. It can help solve crystal structures when single crystals cannot be grown. It can suggest experiments to target new forms that haven't been found yet experimentally, but have been predicted computationally. It can explain certain properties of molecules, for example, the formation of disordered crystal structures or the formation of several solvates. And then it can not just predict whether there is a risk of a late form change, but it can also assess the risk associated with a potential late form change. For example, predicting a potential solubility loss from a more stable but as yet unfound polymorph. How do we use CSP in our company? We perform CSP with the Gray software, which is one of the most accurate commercially available crystal structure prediction engines. And it's always performed in close collaboration with experimentalists. We aim to de-risk all the crystalline forms chosen for drug product formulations. And the aim of this de-risking step is both right-size costly screening work, but also highlights any risk and opportunity associated with the form that is being developed. We compare and discuss computational experimental data between the modeling team and the solid form screening team. And depending on how the data compares, we decide on how to proceed further. Now I'm going to show you two examples of potential crystal energy landscape that we can get from CSP, and I'm going to show you how they would be interpreted in practice. This is not like a real life example, it's like hypothetical. So in this case, in this diagram, you see that the lead form, the form that has been developed for this molecule, is the global minimum, and is the most stable thermodynamically by quite a large margin. In this case, the assessment would be that there is little risk to the form being developed and no extra screening work is needed. And we see this happening in our cases approximately 80% of the times, which is like very good in the sense that this bodes very well for our experimental colleagues, and this is the ideal case scenario. This is the case scenario that you want to be in. The second, the second kind of example that you can have is when the form that is being developed, your lead form, is predicted to be significantly metastable relative to some of its competitors. In this case, the assessment would be that there is a significant risk and that more screening work can be needed. In some cases, it's also possible to identify experimental conditions that could facilitate the formation of these new forms so that they could be targeted experimentally. And we see this happening in our cases approximately 10% of the times. Notice that these two numbers do not add up to 100%, and the reason is because there is like approximately 10% of the cases where the situation is a bit more blurred and cannot be easily categorized in these two buckets. Now I'm going to show you two examples of CSP studies that we did internally to de-risk some of our drug candidates. I would like to point out that for confidentiality reason, I cannot show you the molecules or the crystal structures, but all the data that I'm going to show is real, and the decision that we took and the process and the kind of mental processing that went behind those decisions is historically accurate. So in this case, I'm going to talk about CSP on compound 1, which is a very simple story. So in this case, compound 1 was a drug molecule developed as a one-to-one salt. And the only known anhydrous form of the salt, form 1, is the lead form that is being developed. We performed a CSP studies with 1 unit of the compound in the asymmetric unit cell, or Z'1 using a crystallographic notation. And we also calculated the free energies at finite temperatures for some of the predicted crystal structure by summing to the lattice energy the vibrational component to free energy, calculated with harmonic approximation. So the outcome was that in lattice energy, a match to form 1 was the global minimum, the lowest energy predicted crystal structure, by a quite a wide margin relatively to any of its competitors. And when we went into free energy calculations at finite temperature, we saw that this form remained the most stable even at room temperature, 300 Kelvin. And you can see here that the gap from the lattice energy relative to its competitors to free energy at room temperature increased from 5 kilojoules per mole to 6 kilojoules per mole. So how did we digest this information? Is there a risk to the lead form of compound 1? Both extensive polymorph screens and CSP data agree that only form 1 is possible for this compound. Form 1 is the most stable by quite a large margin at any condition, both in lattice energy and in free energy at room temperature. So we decided that there is no threat to form 1 and that it can be safely developed without the need for adjustments or for some extra screening work in this case. Now I'm going to show you a more complex story, that of compound 2. This compound is basically this candidate drug. The lead form is like an anhydrous neat form, so single component crystal structure. and the only known form is form 1, which is the form being developed. We performed a CSP with 1 and 2 molecules in the asymmetric unit cell, and what we found out was that a match to form 1 was not the global minimum in this case, but it was ranked 5th in lattice energy, approximately 2 kilojoules per mole above the global minimum. So we decided that the best approach was to look at some of the predicted structure more closely. And what we realized by looking at some of the predicted structures is that several of them are not very dissimilar to one another, but there are slight modifications, which we assess that are likely to belong to the same finite temperature ensembles. So basically, they would not be able to crystallize separately at finite temperature, but vibration would likely average them out, and they would belong to the same. Basically, they would crystallize in the same structure at finite temperatures. And this analysis greatly simplified the landscape, because we noticed that, for example, the three lowest energy crystal structures are very similar to one another, and they would likely crystallize as one in the solid state at finite temperatures. And also some of the crystal structure higher in energies are very close to our match to the known form. So we went into finite temperature calculation. So we calculated the lattice energy at finite temperature. And we saw a lot of re-ranking from 0 to room temperature to 298 Kelvin. And what we discovered was that at 298 Kelvin, the global minimum is rank 11, which is a crystal structure that is closely related to rank 5, which is the match to form 1. And at room temperature, there is like all the crystal structures, there are like several crystal structures are very close in energy. So how did we digest this data and came to a consensus? Although it is metastable at 0 Kelvin in lattice energy, a structure closely related to form 1 is the global minimum at room temperature. At the same time, extensive experimental polymorph screen did not find any polymorph more stable than form 1. So we decided to proceed with lead form 1, as the CSP study, despite these complications, did not show any significant risk of a form change at processing relevant temperatures. The second topic I would like to discuss today is the use of CSP as a tool for crystal structure solution. Determining the full 3D crystal structure of APIs and some of their key intermediates is very important. Luca Russo will have a nice talk on this in a couple of weeks, but in general, a full 3D structural determination allows to understand properties of certain solid form states. It helps guarantee quality control by providing a unique trace, a unique simulated powder X-ray diffraction trace to be used for quality control of batches downstream. And in particular for APIs, a full 3D structural determination can be very important for patent protection. However, although single crystal X-ray diffraction is the gold standard for full 3D structural solution, it can often be difficult experimentally to grow single crystal of sufficient quality for this technique. And in these cases, only powder X-ray diffraction or PXRD data is available. However, full structural solution from PXRD data can be very complicated, in particular for molecules of the size and level of flexibility that we tend to deal with generally in the drug industry, the pharmaceutical industry. And CSP can be used to help solve the crystal structures in the absence of single crystals of sufficient quality for X-ray diffraction. How can we do that? If we have an experimental PXRD pattern and some CSP-generated models of crystal structures, it is possible to compare the CSP-generated, the simulated powder patterns of the crystal structure generated by CSP to the experimental PXRD pattern, and then it's possible to refine some of the models that match this experimental pattern against it to get a full 3D structural solution. And also in some cases, the data can be used iteratively, and the experimental data can be used to delimit CSP. As already mentioned, CSP is an extremely costly process. So if the experimental data can be used to delimit the search space to be covered by CSP to find a match, this can greatly simplify the task and reduce the computational burden of this analysis. So how do we use CSP for structural solution internally in our company? So when we need to solve crystal structures and we cannot grow single crystal of sufficient quality, we use the power of solid state modeling. So we've performed CSP with Grace to generate structural models, and then we perform Ritvi refinement to fully solve the lattice. So let's say that we have a PXRD pattern and we need solution. How do we proceed? We can do a targeted CSP, so a CSP with a very limited search space, only aimed at solving the crystal structure. We can do an abbreviated CSP, so not delimited severely just to solve a crystal structure, but also not a full-blown one like you do for a candidate drug. So for example, you can limit the Z prime, or you can just consider certain space groups. And finally, one could also go into a full-blown CSP, generate all structural models, and then perform the refinement and the structural solution at a later stage. So how do we decide which approach to take? That will depend on how much information can be gathered from the PXRD. Can it be indexed correctly to a degree where we can confidently limit the CSP to a very limited search space? And do we need more information from the landscape, about the landscape? Do we just need to solve this crystal structure, or do we also want to know where this crystal structure is placed among some predicted competitors? Is there a risk of a late form change? So this kind of decision making will influence how we approach this problem. I'm going to show you two examples. The first one, we did a crystal structure solution from a very targeted CSP. And in this case, the compound that for which we were trying to solve the crystal structure was the starting material of the anti-HIV drug doravirine, or MK1439. The lead crystalline form 1, for which we had a full single crystal X-ray diffraction solution, underwent an unexpected solid form change to form 2. However, we didn't have we could not grow any single crystal for form 2, but we could only gather powder X-ray diffraction data, and we chose to use CSP just to solve the crystal structure of form 2 of this compound. So starting from the powder X-ray diffraction data, we performed indexing. We basically determined the unit cell dimension and the space group, and this was confirmed by Pauli refinement. Then we performed a very targeted CSP that was limited to the P21C space groups and unit cell dimensions very close to those from the indexing. And as a final step, we compared the crystal structure that we generated to the experimental powder pattern to see if the simulated powder pattern of any of them matched the experimental powder pattern, and this was done with a cross-correlation function method. So in this plot here, I show the results of this analysis. On the y-axis, I'm showing the relative lattice energy of the crystal structure generated by this targeted CSP study, and on the x-axis, I show a figure of merit for the match with form 2 of this compound. A higher value means a better match, and you can notice that there is a very obvious outlier. The lowest energy crystal structure is also the one that has a significantly better figure of merit for the match with Form 2. So we use this global minimum as a starting point for Rydberg refinement, which was successful. And in this way, we were able to fully solve Form 2 and get its full 3D coordinates. A second example is where we did a crystal structure solution, not from a targeted, but for an abbreviated CSP. So in this case, the lead form of one of our key intermediates needed to be solved, but we also had interest in determining the risk of a late form change. So we wanted not just to solve this crystal structure, but we wanted to place it on a crystal energy landscape to see whether there was any threat, any more stable threat. So we performed a Z'1 CSP study. So the CSP study was limited to one molecule in the asymmetric unit cell. And in this way, the aim was both to solve the form and predict any risk associated with it. So this is the outcome of this limited CSP study, so this abbreviated CSP study in Z'1. The crystal structure ranked second in lattice energy, had a very good match with the experimental powder pattern, and could be easily refined against it, and this allows structural solution. Since it was predicted to be metastable in lattice energy, we went into free energy calculation, and we noticed that at room temperature, at 300 Kelvin, this crystal structure becomes actually more stable. So there is little risk of a late form change at room temperature. And as you can see here, the stability changed quite drastically from lattice energy to free energy at room temperature. This crystal structure went from being metastable by 2 kilojoules per mole to be more stable than the lattice energy global minimum by approximately the same amount. And this is a very nice example of how in the same study, we were able both to understand, to solve a crystal structure, but also to understand its landscape, at least within a limited search space. The third and final topic that I want to discuss today is the use of virtual conformer screen for co-crystals. So why are co-crystals important? It is often the case that single component crystal structure of drug molecules have suboptimal properties, in particular suboptimal solubility. Salt formation can often solve the solubility problem. However, for non-ionizable drugs, co-crystallization can be the only suitable option without going into enable formulations. The problem of experimental co-crystal screens is that they're costly and laborious. They're generally based on a trial and error approach, where a variety of conformers are experimentally screened until a hit is found. So can we use modeling to limit the cost of this process by indicating the most promising candidate? So there is the COSMO-RS theory, which is a theory to compute the chemical potential of liquids. And the software COSMO utilizes this theory to calculate the strength of interaction between two conformers. The idea behind this approach is that the strength of the interaction between two conformers in the solid state, which will determine whether or not they will form a co-crystal, can be approximated by the energy of the interaction of the two conformers in the liquid state, in a supercooled liquid state. And the idea is to calculate an energy of mixing, which is a measure of how much two conformers prefer to stay together rather than separate. And the lower this energy of mixing in the supercooled liquid state is predicted to be, the more two molecules are predicted to like to be together, and so the better co-crystal conformer they are predicted to be. How do we use this virtual co-crystal screen within our company? So when there is interest in co-crystallizing a given molecule, we use this modeling technique to guide the screening campaign. We perform virtual screening. We rank the coformers of a given molecule that we want to co-crystallize by the enthalpy of mixing using Cosmotherm. And then we suggest for prioritization those at the top of the list. Here I'm going to show you a retrospective validation that we did on two compounds. One is an intermediate and one is an API. For both of these compounds, all these coformers were experimentally screened before we did the virtual assessment. And in both cases, only one successful coformer existed. And in both cases, the retrospective modeling identified it near the top of the list. So what this means in practice is that if we had applied the virtual method before, we could have gotten the same hit, performing a significantly reduced number of experiments. And so a lot of time and resources would have been saved on performing co-crystallization experiments that ended up to be unsuccessful. So here I'm going to show you an example of how we use this prospectively. So in this case, there was interest in performing on finding a co-crystal of a given API molecule because the single component crystal structure had suboptimal properties. So we performed a virtual co-crystal screening ahead of the experimental work, and the experimental work was partially guided by this virtual screening towards the most promising coformers. So in this table, I show some of the coformers that were experimentally screened. And as you can see, those at the top of the list are in green, were successfully co-crystallized with the API, and those in red were failed experiments. What is interesting to note is that coformer 2 is not one of the coformers that is routinely screened by our screening team, and was and guided by the virtual screening work, was tested and successfully crystallized with our API. And what is very interesting here is that the co-crystal with coformer 2 is actually being considered for formulation, because relative to the single component crystal structure of this molecule, it has both improved crystallinity and improved thermal stability. So this is a very nice example of how performing some modeling ahead of a screening campaign directed towards finding something that was not expected, that is not done routinely, and that has very good properties. So before ending, I would like to provide a summary of what I discussed today and some conclusions. Solid state modeling is becoming an ever more important component of our drug development workflows. It's very important in our company, but it's also very important in the whole pharmaceutical industry. Experimental and theoretical work best in tandem. They work best together. Experimental work without modeling can be wasteful, and modeling work without an experimental validation can be not particularly meaningful. Solid state modeling is an evolving field. Some recent developments, for example, the routine inclusion of free energy calculation in CSP, are proving fundamental to increase the confidence in the data that we get, and in having them influence our experimental work. And what I would like to point out, and I think this is something that I would like to stress quite strongly, is that even when modeling does not directly lead to new discoveries, the identification and the assessment of risks, or the identification of a lack of risks, can be invaluable on its own. So I would like to thank some of my collaborators and colleagues who have been fundamental for all the work that I've shown today. And I would like once again to thank the audience and the organizers for giving me the chance to talk, and I'm ready to take any question.
Thank you, Luca. there is a wonderful presentation on the role of solid state modeling in solid formulations. And I'm sure the audience got a lot out of some of the case studies that you shared on how experiments and theory can go hand in hand to solve problems here. So um, let's go ahead and take some questions. So the first question is, DSC curve of solid solution has single or two endothermic events, especially melting point. Unfortunately,
Can
there's
you
no
repeat?
slide number there.
Can you repeat the question? I couldn't hear.
DSC curve of solid solution has single or two endothermic events.
I would consider them as two separate ones. We have never I never dealt with them in practice, but I wouldn't consider them as part of as a crystal structure, some unique phase. But I've never had to deal with that in practice.
Okay. The next question is, have MD simulations been applied and compared to DFT calculations?
We don't use MD simulations routinely in our modeling. They have been applied, yes, and there are some very nice publication on it, but we do not apply them internally. They can be used in some cases, and they're very good to understand how temperature effects, for example, average, like that aspect that I talk about ensembles of crystal structure that are separate at 0 Kelvin, but they can be averaged out by vibrations. They can be used for that. We haven't used them internally in our company, no.
Okay. The next question is, does CSP predict neat polymorphs only, or hydrates or solvates too?
It can predict anything as long as within reason, as long as you give it in the input file. But you need to specify in the input file what you're looking for. So if you want to predict solvates, you need to specifically tell the code that you're looking for a molecule and a solvent molecule, but it can do that, yes. You need to also specify the stoichiometry. So if, for example, if you're looking for a monohydrate, you need to specify that you're looking for a 1-to-1 ratio. For a dihydrate, you need to specify that you look for a 1-to-2 ratio, but it can be done, yes.
Okay. The next question is, how important is free energy of vibrations with temperature correction?
It is extremely important, and we are realizing it more and more. Lattice energies are very accurately predicted, but of course, stabilities can be significantly altered by vibrational effects. There was a survey performed like some time ago where it's shown that quite a large proportion of polymorphic pairs are re-ranked by thermal effect. So it's extremely important. And it's good that the tools to compute it are becoming more accessible and more accurate with time.
This is a question related to slide 9.
Yeah.
Could go to slide 9. The question is, how do you determine the number of units in the asymmetric unit? That is pretty much the Z prime, I guess.
Is it here? Okay.
Slide 9. Yeah. Maybe the next slide, I think. Yeah.
Yes. It's a choice that you need to make when setting up the CSP study. Statistically speaking, the great majority of crystal structures are with Z prime of 1, so with 1 unit in the symmetric unit cell. Higher Z primes can be important. So the choice will depend on what compound you are dealing with. For example, an antipure crystal structure tend to have a larger proportion of larger Z primes. It will depend on computational cost. Of course, adding basically performing CSP studies with larger Z prime values are more expensive, and they scale very, they scale very badly. So performing a Z prime 2 study is not twice as expensive as Z prime 1, can be significantly more expensive. And for this reason, it really depends on what system you're doing. For example, in this case, since it was a salt, which contained two components, we decided to only go with a Z prime of 1, because doing Z prime of 2 would have been computationally affordable. So it's a choice that will depend on a variety of factors, but it's something that needs to be specified when setting up the study.
Okay. The next question is, how do we know from CSP if more stable polymorphs can exist in normally accessible conditions? For example, more stable polymorphs with lower energy and higher density can sometimes only be produced from challenging experiments, for example, high pressure crystallography. Can you comment on that?
That's an extremely good question, and it's very difficult at times, in particular because crystallization is strongly affected by kinetics, and kinetics is not easy to model. So for these reasons, understanding how a predicted form can be accessed, or if it is accessible at all, is sometimes a bit of a matter of historical understanding and trial and error. In some cases, some experiments can be suggested. For example, if there is a crystal structure of a related molecule that is similar to one of these predicted forms, you can say that it can be used as a template or a seed for that form. But it's not always possible, unfortunately, to know how to access some, or if some of these forms are actually accessible at all.
Okay. The next question is, how do you determine or measure similarity between structures? This is related to slide 13.
Yeah, let me go there. There are a variety of ways to do that. What we tend to do is to use the crystal packing similarity tool available through either Mercury or the CSD Python API. So we try to overlay basically the crystal structures, and we try to compare whether they are similar, they can be matched, or they cannot be matched, with various level of similarity thresholds. Another thing that can be done without performing like an atom to atom comparison, one can compare the unit cells. So if unit cell dimensions are extremely similar, it's possible to then go into a bit, get into the detail and see what actually differs between them. So you can either check the crystallographic parameters, but I would say the most accurate way is to try to overlay the atoms with some of the tools that I described.
Okay. The next question is again related to slide 9. What
Yep.
is the maximum complexity of molecules that you perform CSP for? And is there a correlation between the degree of complexity of the molecule versus the outcome, where you can classify a project as a no worry case or a problematic case with respect to the results from the CSP ranking?
That's an extremely good question once again. Well, the level of complexity, the maximum level of complexity is at the end a matter of the resources that one has at his disposal. If someone wants to throw more resources, the complexity can increase. This said, I personally I haven't ventured in anything with more than 80 atoms or 10 flexible degrees of freedom for the single component. Of course, if you have more than one component, you can afford probably even less. And Z primes larger than 2 are generally not done because they're way too expensive. Also because they're quite rare, but they are unaffordable. So I would say the limits are these ones that I've outlined. Something like 80 atoms, I would say, becomes very difficult, but this will depend on the resources.
Okay. The next question is slide 15.
Yeah.
Can you identify an anisotropic or monotropic relationship using CSP for the polymorphs?
You can predict it. There is a very nice paper from Yuri Abramov that shows that this prediction has a very large error bar because it has like the prediction of the because of the way the errors are calculated, the prediction of a temperature at which a transition occurs is very hard. But yes, it can be an anisotropic transition can be predicted if for example, for the intermediate that I was discussing, that we did both structural solution and understanding where it plays on the landscape. That is a case of an anisotropic transition because we predicted that at 0 Kelvin in lattice energy, there is a different global minimum that there is at room temperature.
Great. Next is slide 18,
Yep.
18. Which X-ray source is used? If copper or molybdenum is used, what is the minimum acceptable R factor?
That's a question I cannot answer. I wouldn't be able to give you a minimum threshold here. However, what I can
Okay.
say is that if the powder pattern is not of great quality, there's a lot of preferred orientation, it can be very complicated to perform solution. But I cannot give you a threshold.
Okay. Next question is, what if the PXRD comes from a mixture of different polymorphs? Is it possible to resolve the individual polymorphs?
It's much more complicated. I think there are ways to do that, but it becomes into like it gets into a realm that you probably cannot do with the very simple workflow that I've shown. You probably need some more sophisticated tools that I think are being developed, but it becomes much more complicated.
Okay. The next question is, what aspects of CSP do you think that needs to be improved?
I mean, unfortunately, I'm a user, not like a developer, but I think something that would be very nice would be to have more accurate energies to start with. So to get to a point where one does not even need it depends on the cases, but it would be nice to have a kind of a way to get more accurate energy from the search without having to go into the very expensive electronic structural calculation. This said, I don't know exactly how achievable that would be. That would require quite a lot of effort. But I think that because that would significantly reduce the computational burden of the study. So getting a better energy in the search would be a very good development, I think.
Fair point. The next question is regarding the targeted or abbreviated crystal structure prediction that you mentioned. The question is, would you also envisage the use of some form of low-cost, high-throughput solution at candidate selection stage with the aim of discriminating among ideal versus problematic landscapes from different candidates?
It's a matter, once again, it's a matter of resources. So it's something that ideally, like even in our company, but I believe in other companies as well, there is an interest in pushing CSP at to an earlier stage. I didn't understand exactly in what context this question. Is it like a question about when I'm like before candidate selection, when a molecule is in the discovery space?
Yeah, like when would you find it extremely useful to use those kind of approaches?
If it was possible to do like a very high throughput study that allows to understand a landscape of a molecule very fast, I think it would be very useful to apply it even in the discovery space when you're selecting a candidate rather than having already a candidate. And if you could use modeling and CSP to inform the actual candidate selection, so it was basically selecting a candidate that already is known to have good solid state properties or not to have a problematic solid for landscape, I think that would be a great development. And there is nothing technically that makes it impossible these days beside resources.
Great, can't agree more on that. The next question is, how much computational resources do you typically use for these calculations, and how long do these calculations take to complete?
I showed that like a CSP study can take hundreds of thousands of CPU hours. So in practice, that means using a few hundred CPUs on a high performance computing for what can be weeks to a few months. That will depend. And it will also depend on the scope of the study. So for example, the crystal structure solution, the targeted crystal structure solution study that I showed before, that was really quick. That took like a few days because the CSP was heavily limited by the experimental information. So it really depends on what we are trying to achieve. But if you're talking about a full de-risking study for a candidate drug molecules, a few weeks to a few months on a few hundred CPUs.
Okay, let's do some rapid fire questions because so some questions for Cosmotherm related stuff. So does
Yep.
Cosmotherm only perform enthalpy, excess enthalpy, and not delta G?
It does both. It calculates both delta G and enthalpy, but we have found enthalpy sufficient for most of our applications, so we tend to use enthalpy.
Okay. Can Cosmotherm provide guidance for conformers for salts?
I believe it can technically, but I don't think it's ever been tested for charged compounds. It's always been tested for neutral. So I wouldn't guarantee the accuracy of this approach.
Okay. Time for two more questions, and both are related to slides 27 and 28. So the first question is, did you calculate the degree of enrichment from the virtual screen for conformers? For example, if you create an ROC plot, what is the area under the curve or sensitivity and specificity?
I did not. I mean, I did actually calculate an enrichment factor that I cannot recall on top of my head. I didn't perform an AUC analysis for this, so I wouldn't be able to answer that. But we looked at it qualitatively, and we noticed that in both cases, the amount of time that could have been saved for at least these two examples was quite large. But I didn't perform any more complex statistical analysis. No.
Okay. This is probably the last question for the session today.
Yep.
Have you investigated whether the co-crystals not experimentally formed were due to the fact that the main conformations in the selected solvents were not those used in the Cosmo calculation? Again, related to slides 27 and 28.
The Cosmotherm calculations actually use conformational ensembles. So it takes basically an ensemble of low energy conformation, which are more likely to be present in solution. So I wouldn't think that is a reason why that was the case. I think is a much more likely reason is that these enthalpy of mixing calculations have quite a lot of assumption in them. For example, you are only considering short range interaction in a supercooled liquid rather than long range interaction in a solid. So I think a much more likely explanation is not the conformer ensemble used in the calculation, is more the assumption that are quite inherent in the procedure.
Great. Thank you, Luca.
And thanks once again to everyone for listening and to the organizers.
Thank you, Luca. Really appreciate it. We still have a few more questions that will be answered by Luca and at a later date and will be posted along with the recording on our website. Once again, we'd like to thank the speaker today for the wonderful presentation in bringing the solid state modeling and its role in drug development to the forefront. So a lot of participants have asked me where to find the recording. So once again, I just want to mention that if you visit excelpi.com under the events page, if you click on FSF 2021, both the recordings from the previous two webinars are available there along with the Q&A page. So you just have to click on the play button and then follow the instructions, and then you'll be able to watch the recordings. And some of the participants have asked whether the slides will be available. Unfortunately not, only the recordings are available. Okay, so you can find everything on our website. So before we end the session today, I just want to alert you about what's coming up next for webinar number 4. We have Dr. Daniel Joseph Price from Millipore Sigma. Daniel is a strategic marketing manager at Millipore Sigma in Germany. And he's going to talk about amorphous formulations for solubility enhancement, risk, and opportunities. And as you all know, Daniel is a strategic marketing manager for solubility enhancement and sustained release excipients portfolio. Daniel plays a leading role in several key innovation initiatives, including 3D tablet printing and computational formulation development. So next week, Daniel is going to share his expertise in mesoporous silica and thermodynamics of amorphous formulations. So please stay tuned for next week, and don't forget to send in your comments and questions. We are planning to reach out to a few of our participants to get some feedback and also learn about the topics that could be covered in the next edition in 2022. Because we are also planning to release a newsletter after this FSF 2021 event. And for those, if you want to know whether there are still more seats available to register and participate, of course, there are a lot of seats available because we extended the limit, the seating capacity from 750 to 1,000 this year. So currently we have over 770 participants registered, so there's still 200 seats available. So please spread the word with your friends and colleagues in the industry, and please reach out to me if you have any questions or comments. Looking forward to seeing you all next week. Until then, take care, stay safe. Thank you very much. Bye.